All right, everyone. Well, welcome to the most recent iteration of these live weather and climate office hours. As I've reflected on really throughout this season, I am doing these quite a bit more frequently than I expected to, multiple times per week in this exceptionally active winter in California. This really has been kind of an incredible weather year. In this part of the world, and there's more yet to come. It's still not over. Since last we spoke, there have been all sorts of extreme weather in California. Everything from a very strong windstorm along parts of the Central Coast and the Bay Area. This was associated with the double-barreled storm system last week that explosively deepened right near the coastline and sort of defied early predictions to become much stronger than expected and have much greater wind impacts in the San Francisco and Monterey Bay areas last week than had initially been anticipated. That storm, in some retrospect, and this has been really interesting to see meteorologically, it even took on some hybrid storm characteristics. So I talked last time about how extratropical cyclones are structurally and fundamentally different from tropical cyclones in the sense that extratropical cyclones derive their energy from horizontal energy imbalances in the atmosphere, and tropical cyclones derive their energy just from the warmth of the ocean and the latent heat fluxes out of large bodies of water. Well, that was slightly oversimplifying. There are such things as hybrid storms that have components of each, essentially, where you can have extratropical and tropical-like characteristics in the same cyclone. Well, several meteorologists, after taking a closer look at what happened last week in California, noted that the storm during its explosive deepening phase right off of the Bay Area, did develop some hybrid-like storm characteristics. In other words, it essentially had a warm core, although this developed by a very different means than a tropical cyclone would. So, of course, the water temperature off the coast of California is nowhere near what it would need to be to sustain tropical cyclogenesis. The water would need to be literally 20 to 30 degrees warmer, so it's just not even in the same universe. However, what happened last week was apparently a fairly unusual process along the West Coast called warm seclusion, where the cold air behind the storm actually outran the warmer air near the center of the storm. So essentially you ended up having a center of the storm that was warmer than all of the air in all directions surrounding it. Tropical cyclones are warm core cyclones, and extratropical cyclones are usually cold core cyclones. So in this case, we had an extratropical cyclone that had a warm core due to this very unusual warm seclusion process. And this is probably why in last week's office hours, we were all just sort of sitting there, myself included, sort of looking at the live radar screen, somewhat in awe, because that storm looked an awful lot like a tropical cyclone, even though, again, it was not a hurricane, it was not a tropical cyclone, but it did have more tropical cyclone-like characteristics, I think, than some folks had originally realized due to that warm seclusion process. And so we did essentially have hurricane-force winds along some portions of the coast. The wind damage in the Santa Cruz Mountains was very severe. There were gusts in excess of 80 miles an hour, and I don't think we quite got to sustained hurricane-forced winds of 74 miles an hour, but we certainly saw gusts, widespread gusts, well in excess of that level that brought down a huge number of trees. There were actually essentially some timber blowdowns. So where you drive down a road and every 100 or so yards there's a new tree down, and this includes tall redwoods that didn't just get uprooted by the force of the winds with wet soil, but also got snapped at the base, and that is indicative of much stronger, more violent wind gusts than you would normally expect. So this is a bit more of a meteorological curiosity than anything else, but I think the fact that we hadn't seen anything like that on the radar screens in Northern California in a long time, if not in living memory, is perhaps supported by this idea that it did undergo an unusual hybrid cyclogenesis where there was warm core at the center due to warm seclusion. Not because the ocean was warm. In fact, right now the ocean is even colder than usual off the coast of California, and it's already pretty cold to begin with this time of year. So that wasn't it, but it was due to the unusual dynamics of the storm itself. And it's an interesting indication of a storm development process that I personally hadn't thought a lot about, off the coast of California anyway. But we do actually see some evidence in our arc storm scenarios, for example. A couple of the storm systems that occur in those extreme storm and flood scenarios that we've developed for the state of California, when we downscaled them and morphed, a couple of the storms kind of look like this. So that's interesting to consider, especially in a warming climate. But I don't want to spend too much time on that today because there's so much else going on, and that's just what happened last week. Last week's storm also brought yet more supercell thunderstorms to the Central Valley, and notably a damaging tornado within the city limits of Los Angeles, which is rare for California. An EF1 tornado which tore off roofs, knocked down water towers, and caused even an injury, which is again unusual for a California tornado in Los Angeles last week. So there's been severe convective weather, there's been thunderstorms, there's been more snow, there's been more flooding, landslides and mudslides, wind damage, just about everything you could imagine. It's happened in the last week in California weather. Meanwhile, the Central Valley, especially the San Joaquin Valley, mostly the Tulare Lake Basin, in fact, continues to have worsening flood problems, with the old Tulare lake bed starting to fill in. Unfortunately, that includes some smaller communities within and near that lake bed. And there's all sorts of contentious political considerations, I guess you could say, when it comes to what's happening in the Tulare Lake Basin, where there's some very powerful agricultural interests who essentially, because of the nature of the land ownership, have a certain amount of power in terms of engaging in unilateral actions that might actually harm adjacent communities. And unfortunately, that is what we've seen, where some of the large landholders in the area have made decisions about which land to flood first that floods some communities at the expense, so essentially prevents flooding initially in some agricultural areas at the expense of local communities. It's not quite that simple, and unfortunately the reality is all of these areas are likely going to flood eventually this spring as the flooding continues to worsen. But I do think it's important to contextualize a lot of what's going on as not just related directly to the weather. This is where the weather and land use and agriculture all begin to converge in a very obvious way and in very complicated ways that have a lot to do with the history of the region and the embedded inequality, the socioeconomic inequality, and these low-income and farm worker communities that are the ones most immediately at risk from these floods. Later this spring, that risk is likely to spread well beyond these areas into much larger, potentially closer to larger population centers in the San Joaquin Valley, although that's, at this point, it remains speculative exactly how far that risk spreads. But suffice it to say that right now there's more and more water pouring into the Tulare Lake Basin, and that water is not going to be leaving the basin for the foreseeable future, even as inflows continue to increase in the coming weeks. And the reason why these inflows are going to continue to increase is, well, first of all, we remain in a fairly active weather pattern. An additional storm is going to come tonight into tomorrow. I'll talk about that a little bit in a moment. But there is also just a tremendous amount of water stored in the snowpack up in the High Sierra. In fact, that snow water equivalent in the Southern Sierra, particularly in the watersheds that eventually drain into the Tulare Lake Basin, those snow water equivalent is just continuing to increase. It's just going up and up and up, and we're almost in April, and it is still increasing and will probably further increase noticeably this week. That's kind of amazing if you think about what time of year it is and what kind of snow year we've already had. to see even more snow accumulating on top of that is just incredible. So again, to reiterate, we're now well beyond historical records in terms of snow water equivalent in the southern Sierra. Certain basins more than others. Notably, we're nowhere near record snowfall in the northern Sierra, but we're well above the previous record in the southern Sierra. The central Sierra is somewhere in between. Very large snowpack there as well. But I am mostly concerned about the San Joaquin River watershed, so the southern half of the Central Valley, because the snowpack, A, is not nearly as extremely large in Northern California as it is in the Central and Southern Sierra, and also the flood control system along the Sacramento watershed is, frankly, better up to the task of handling a challenge like this. The San Joaquin watershed is in trouble this year, both because the snowpack is much larger in absolute terms, historically large. Conditions are already very wet, so reservoirs are already essentially full in some places, and there's already downstream flooding. And also, the reality is the flood control systems on the San Joaquin watershed are just not as robust as they are on the Sacramento. So this is an area that was already more vulnerable to begin with. This year it's been hardest hit by storms, and now they've got a record snowpack, with all this latent snowmelt yet to come. Again, we're still accumulating more snow than we're melting, so the amount of water that's stored up there to melt later is ever increasing. And there's a lot of folks who've been asking specific questions about volumes. It's really difficult to know, except that, the reality is all of that snow is going to melt and end up in the Central Valley between now and, say, June. With some melt continuing into July, but the vast majority of that snow melt is going to happen between now and the end of May. And it is all going to end up eventually flowing into the San Joaquin River, or at least into the Central Valley, and then into watersheds that drain into the San Francisco Bay Delta, and therefore eventually into the ocean. But it's got to pass through the Central Valley first, and the Southern Sierra, the Western Slope tributaries are going to be dealing with it. The smaller but important reservoirs there are potentially going to be releasing a lot of water and are going to become increasingly difficult to control operationally. This is going to be potentially a big story. So again, the flood situation in Tulare Basin is going to get worse before it gets better, and it's likely also to get worse along many of the San Joaquin River tributaries, and perhaps along the San Joaquin River itself later this spring. I don't know when it's going to peak. Again, as I keep telling folks, it's really a question of how severe the flooding gets rather than will there be flooding, because of course there already is flooding. It's likely to get worse. The question is, will it get really, really severe on a widespread basis? And that we don't yet know. It's going to depend on how quickly this melts. If we get lucky and it's all gradual, that's probably the best case scenario, but there would still be widespread, perhaps moderate flooding throughout the region. If it melts quickly, perhaps we get a late season atmospheric river that's warm in April or early May. Unlikely, but not impossible. Or we get a big early season heat wave, as I mentioned last time. That could also cause rapid melting. Either of those scenarios could result in much more severe flood conditions in the San Joaquin Valley this spring. Additionally, irrespective of whether one of those two things happens, but especially if they happen, there could be infrastructure failures, there could be levee failures along more critical flood control parts of the system further downstream, due to the persistently high flows. Even if we don't get a record-breaking crest, or we don't get any levee overtopping or anything like that, that still assumes that the levees are capable of withstanding extremely high flows for weeks and weeks and weeks on end. Hopefully they do, but there's no guarantee there won't be any problems there. And we know there are certain weak spots in the system, and this next few weeks to the next couple months is going to test those weak spots on the San Joaquin Valley Flood Protection System levees. So, all of that is to say, it's been a hell of a year in California weather, and it isn't over yet. There's still more to come. All right, I want to talk a little bit about the storm that's immediately inbound. I have that open on satellite imagery, and perhaps maybe I'll even try. Let's see if I can try pulling that up like I did last time with the imagery in the corner of the screen. So let me just see if I can throw that out here and get that up on the screen for folks to see. It looks like that will work. Alright, I'll do the same thing I did last time. I'm going to have this down in the corner of the screen. Yeah, there we go. I kind of like how this works. It's kind of fun to have something like this in the corner. So it's not quite as visually dramatic as the giant spinning bands of rainfall and the Fujiwara interacting vortices from last time. But it is nonetheless, I think, interesting to see the evolution of yet another significant storm system, which may undergo, once again, rapid cyclogenesis, although this time it's going to occur much farther off the coast. In fact, it looks like the low-pressure system that enters a rapid deepening phase is most likely to do so west of the Oregon coast. So this is going to be not going to affect Central California nearly as severely as the last one. But this will be yet another moderate to strong storm across most of Northern California. The strongest winds are going to be along the north coast, so up by Eureka. There'll be gusty winds all the way down Mendocino, Central Valley, and into the Bay Area. And so there could be additional issues, just given how much residual damage there is from winds that have already occurred, how saturated the soils are. There will probably be yet more downed trees and power lines and power outages, but I don't expect the violent 80 mile per hour wind gusts that we saw with that very close range rapid deepening of the low pressure system last week. So I don't think there's going to be a repeat of that, even though the impacts from the storm will be higher than a storm of this magnitude would usually be, just because there's been so many strong storms that have preceded it. So again, strongest winds maybe gusting up to 60 or 65 miles an hour along the north coast. Still gusty, but weaker winds down into the Bay Area, maybe 40 or 50 miles an hour locally. So again, that's enough to bring down some trees and power lines given how wet things are, but it's not enough to produce widespread severe damage in all likelihood as we did last week. There will be more heavy rain, again, in Northern California associated with this incoming storm system. Fairly reasonably low snow levels, actually. This will be yet another cold storm, so I guess the good news is it isn't going to really melt any snowpack. The bad news is going to bring more low-ish elevation snow to places that probably don't want any more at this point, down to around 2,000 or 2,500 feet. There's actually a winter storm warning in effect for the northern Sacramento Valley down to around 500 feet, so that does include Redding, because there's cold air trapped in the north end of the valley, and precipitation is likely to start as snow there. So there could be some accumulating snowfall during this event in the city of Redding. That may be one of the latest, if not the latest, significant accumulating snowfalls on record in terms of lateness in the calendar year, because today or tomorrow it's going to be either March 27th or March 28th. It's pretty late in the season to be seeing snow at the northern end of the Sacramento Valley. So that's going to be a pretty dramatic consideration up there, given the lateness of the season. We're not going to see widespread low snow like we did earlier in February, so this isn't going to be like the February event, but this will be a more localized event up in the far northern end of the Sacramento Valley, although it could be quite high impact up there. Let's see. Yet more rain, yet more heavy mountain snow, more travel disruptions. The last couple weeks have been a little bit quieter up in the High Sierra, so folks have had a bit of a chance to dig out, although again, there hasn't been much thawing. So there's still enormous snowbanks, even though the streets are a bit clearer than they were a few weeks ago. Another few feet of snow up at the highest elevations is just not what people want at this point. It's going to add to the snowpack that's going to have to melt later and cause more flood risk in portions of the Central Valley. But it's also just kind of a big mess right now, all throughout the mountains that have just seen so much snow this winter already. It's gotten quite old for a lot of folks and quite difficult, just day-to-day living up there. So again, another moderate to strong cold storm. No real strong atmospheric river associated with this one. You could probably define one, but it's not going to be particularly notable for its atmospheric river characteristics. This is more of a cold extratropical cyclone type event that won't be as intense as last week's, but could bring significant impacts nonetheless, given the context of what's come before it. The other thing is that this storm, the parent low pressure system, it's actually going to be weakening on approach to California rather than strengthening like last time, which is one reason why the winds won't be as strong, why the storm probably won't throw quite as many curveballs. But nonetheless, the center of circulation is going to get close to the California coast, and it's actually going to slide down the coast offshore. That's going to drag cold and unstable air inland over California and probably result in another round of showers and scattered thunderstorms across the interior and across coastal areas. So this is a pattern that may once again be favorable for some supercell thunderstorms in the portions of the Central Valley. The Central Valley, by the way, has seen more severe thunderstorms so far this season than the High Plains, which is quite remarkable. The season's early, it's only late March, but still, there have been some very High Plains-like supercells in the Central Valley so far this season, and I suspect that won't be the last time. Later this week will be the next candidate for that. And there could even be a period of some thunderstorm activity on an isolated basis in coastal Southern California. And again, this is the kind of pattern that is at least hypothetically favorable for another week spin-up or two. So I wouldn't be entirely surprised if there were another EF0 or EF1 tornado somewhere in California this week with this storm system coming through. So another significant storm. I don't think it's going to be a big storm for Southern California, but there'll be some showers and there could be some interesting thunderstorm activity. It'll be a more significant storm for the northern third of the state, maybe down south into the Bay Area, but not as big as last week's. But again, it's becoming more and more remarkable because we're getting pretty late in the season. This is late March. Climatology usually suggests that precipitation starts to taper off this time of year. Not always. Sometimes you can get a wet April or a wet May in California. But in general, even though these storms aren't exceptional necessarily by winter standards, they become increasingly exceptional by spring standards if they continue to be at this level of coldness and intensity that we continue to see. And in fact, right now, I keep looking for sustained signs of a warmer, drier pattern, and I'm still not really seeing it right now. I don't necessarily see a continuous onslaught of storms like we've seen, so I do think the storms are going to become progressively more spaced out and probably somewhat weaker. But frankly, they still look pretty cold and more substantial than you'd usually expect for late March going into early April for the foreseeable future. So I still see a wet pattern continuing into early April and a fairly cold pattern. So it doesn't look like there's going to be major snowmelt over the next couple of weeks. There'll be some just because of the sun angle increasing on days where it's sunny in between storms. But I actually think that the snow water equivalent 10 days from now might still be higher than it is today. And so this year, April 1st, which is usually the traditional peak of the snow season, or at least the snow accumulation season before things start to melt, it might not be this year. It might be a little bit after April 1st this year with continued accumulation. And of course, that just means that all of the flood forecasts we have right now don't yet account for the precipitation that's still going to accumulate as snow over the next couple weeks. So I would not be surprised if some of the current inflow and runoff forecasts are even a little bit too low relative to what will actually happen if we do get another few inches of snow water equivalent accumulate up there over the next week or two, and then that melts later this spring. Whew, a lot going on. One other comment I wanted to mention is that there's been some public statements by the California Geological Survey regarding landslide risk, and this is something that's worth emphasizing. We have started to see some evidence of more deep-seated landslides. So these aren't shallow surface mud flows, which can be very dangerous, by the way, still, but they're different features. Mudslides usually happen fast. You'll get something, and they happen, essentially, it's usually involving material from the top few feet of soil in an area that can start to slide downhill very quickly. Mudslides and debris flows are usually faster moving than deep-seated landslides. Not always, but generally speaking, and also shallower. And although they can all be dangerous and destructive, deep-seated landslides are a little bit different because there's often a little bit more warning. You start to see cracks in the ground, either at the top of a slope or on mid-slope. Things start to slump gradually before they start to move more quickly and more substantially. So we've seen these. There have been some roads closed in both northern and southern California with these deeper-seated landslides starting to emerge. And they can be quite damaging. The only saving grace is they sometimes occur relatively slowly, and so there's some time to get out of the way and deal with some of the consequences rather than mudslides, which can happen in a matter of seconds to minutes. But there is going to be a growing risk of deep-seated landslides, and those come from when the soil column becomes completely saturated down to deep levels. So mudslides can happen, debris flows can happen when the soil column is actually quite dry except at the surface, and it gets very wet very quickly with excess precipitation over a short period of time. Deep-seated landslides can occur when it's not even raining. In fact, they can occur for months after the rains stop. In California, there's a history of these events occurring into midsummer following very wet winters because it takes a very long time for the deep soil column to dry out. And they occur literally because very wet, deep soil columns are much heavier than very dry soil columns. So even if hillsides were stable under dry to medium wet conditions, under extremely wet conditions, the slopes literally become top-heavy and can start to slide downhill. So it's all about the mass of the soil column, and the more water that gets absorbed into it, the greater the risk of deep-seated landslides. And I know the folks at the California Geological Survey have been emphasizing that risk doesn't go away when the rains stop. In fact, it's somewhat lagged. It often peaks after the rainy season itself peaks. So that's going to be something to watch over the coming months. The risk of debris flows and mudslides will probably go down. They'll go up a little bit again with the storm coming in tonight and tomorrow in Northern California, and then they'll go down again as precipitation tapers off afterward. All right, I'm going to start taking a look at the comments as they're coming in fast and furious. Yeah, question from Charles about what the summer's looking like. It's a challenging question because we've had a year where the seasonal forecast was not good and very different things happened in California for reasons that at this point are not entirely clear. But I do think what's clearly happening is there's a rapid, dramatic transition in the tropical Pacific Ocean from La Nina to El Nino ongoing right now. In fact, there are very warm waters now off the coast of Peru that are causing unusually heavy precipitation in the deserts there and flooding. That is a classic precursor to a significant El Nino event. And right now the atmosphere and the ocean are both in sync and screaming El Nino rapid development over the next few months. So we probably are going to see a rapid shift towards El Nino conditions in the tropical Pacific between now and midsummer. What's interesting is that the ocean temperatures off the coast of California right now are quite cold relative to average for this time of year. In fact, in terms of the relative anomalousness of cold, there is no place on Earth right now that has larger negative ocean temperature anomalies than the west coast of North America. That doesn't mean that the water is colder off the coast of California than anywhere else, but it means it is colder relative to the local average compared to everywhere else on Earth. That's remarkable right now because global ocean temperatures last week reached an all-time observed record high. So if you average over all the global oceans, as of this week, they're warmer than they have been since we've been observing ocean temperature records going back about a century. That's pretty remarkable, especially given that the ocean off of California is right now cooler than average, so it's pulling the global average down in the opposite direction. Despite that, everywhere else it is so warm that it's at a record high globally. Part of this is being driven by very rapid warming of the tropical Pacific Ocean in the canonical El Nino region, but also very warm temperatures in some portions of the Arctic Ocean. So California right now is a really remarkably anomalous outlier. And the western United States, which has seen an unusually cold winter, in fact, in some cases, the coldest winter in a few decades in some parts of the western U.S., are in extraordinary contrast to almost all of the rest of the northern hemisphere, which has seen extraordinary and in some cases record-breaking warmth all winter. It's just been that the one cold patch in the northern hemisphere has been anchored persistently along the west coast and the western part of the United States this year. I don't know exactly why that is this year. That'll be interesting to figure out later. But my point is that the rest of the world is really, really warm right now, and the oceans are astonishingly warm right now, except the ocean right off the coast of California. And I bring that up in the context of the summer because I think that might change rapidly. It does look like the ocean will continue to be unusually cool through April and perhaps through May, but at some point between May and July, I would expect that this would rapidly change. The nearshore ocean in California is likely to become significantly warmer than average by mid to late summer as a significant El Nino event develops. And so this may mean that we have a pretty solid May and June gloom season. I don't know if the warm waters would arrive by that point. But by later in the summer, there could be a dramatic transition where we've gotten used to waters that are unusually cool this winter and spring that could be unusually warm by as soon as late June or July. So we'll see how that evolves, but I do think that there will be something of a moderating influence. So I don't think that the likelihood of early season heat waves is perhaps as high this year as it might have been in some recent years. However, I'm not sure that logic will hold much past June. I think come July, August, and September, we could be once again seeing some very warm, if not record-breaking temperatures in some parts of the western U.S. But I do think the next couple months look probably unlikely to be unusually warm, and April at least could be yet another cool month. Although, of course, cool is relative. April will still be warmer than March was, even if it's below average, just because of the progression of the seasons and the increase in sunlight. So the summer, it's hard to say, except that I think there's probably a somewhat lower than average chance of early season heat waves due to the cold ocean nearby, and also inland because there's such an incredible snowpack and so much water. There will be some, we call it a negative or a mitigating feedback this year. During the drought years, we were talking about positive accelerating feedbacks in terms of the dry land allowing for more heating by the sun and greater high temperatures, which we saw last year. We saw all-time record high temperatures in some parts of the Central Valley and the Sierra foothills. Right now, with a record snowpack in the Central and Southern Sierra and very wet conditions in the Central Valley, including potentially widespread flooding in some areas lasting into June, that will have a mitigating influence on temperatures because there'll be a lot more water around, or there might be snow around at the higher elevations later into the season than usual. So I think cooler than average start to the warm season, if you will, between April and May and maybe into June. But then all bets are off later in the summer, as much warmer than average ocean temperatures may suddenly emerge, as El Nino may send a Kelvin wave or two, coastally propagating Kelvin wave up from the tropics. That can happen during these sorts of events. It might decrease upwelling and increase ocean temperatures along the coast of California. So stay tuned. I'll have a longer conversation about that later once we get a little bit closer. But there's still so much else to get through in the meantime. I'm going to focus on that for now. All right. Let's see here. Going through some more questions. Yeah, there's a question from Ash about how in a warming climate will hybrid cyclones become more plausible or probable, and will ocean temperatures rise enough within our lifetimes to support these happening with more frequency? It's a very interesting question, and as I kind of pointed out right now, this most recent warm seclusion hybrid cyclone event last week off the coast of California really didn't happen because the ocean was warm. In fact, it was actually colder than average. So this is an indication that you can get these sorts of storms even if the nearby local ocean isn't really very warm at all. In fact, even if it's quite cold. But there is a deeper question there that's interesting, is there some mechanism by which these might occur more frequently in a warming climate? And I personally suspect the answer is yes. I don't think we'll see them very often, but they do pop out at some of our future warmer climate downscaling simulations, things that look an awful lot like this. And my colleague, James Doan at NCAR, actually, who was looking at some of these arc storm simulations, sort of happened upon these when he was looking at some of the data, and we kind of both looked at these together with some eyebrows raised. We don't have a good answer for that yet, but maybe somebody will take a look at it in the next year or two and we'll have a better answer. I do think that warming oceans will slightly increase the likelihood that recurving tropical cyclones during the warm season, so essentially East Pacific hurricanes, sort of like the one we had last summer that made it pretty close to San Diego as an intact tropical storm and brought major warm season rain and wind impacts to Southern California, it will increase the likelihood of seeing remnant storms like that. Or perhaps, it's not implausible that in a future where the ocean is a degree or two warmer than it currently is, that you might actually see a full-fledged tropical storm or even a weak hurricane making it pretty close to San Diego or even Los Angeles someday in the warm season. That wouldn't happen in winter, though. That would be something that would happen probably during a strong El Nino year, because it means that the nearshore waters in Southern California are often a few degrees warmer in those years. So that might be an interesting conversation for later this summer if a strong El Nino emerges. But I do think there's a plausible mechanism that we might see more storms like that, even though I don't think that they're ever going to be common. And again, to differentiate between the extratropical cyclone that has some characteristics that look a little bit like a tropical cyclone from an actual tropical cyclone, which would require very warm ocean temperatures, which, as I mentioned, we're at least 20 to 25 degrees Fahrenheit too cold in the ocean to see something like that at this time of year in this part of the world. So, even a lot of warming would not get us to that point. But to the other points, I think that's a fair question. Let's see here. Yeah, there's another question from Rachel about how many acre-feet of water would it take to refill the aquifers in the Central Valley? Will the floodwater sink to the water table? I don't have specific numbers, and to be quite honest with you, I don't think anybody knows really what those numbers truly are, although some folks may be able to offer sort of order of magnitude ballpark numbers. I can't even do that. I'm not a hydrologist, but I will say that there are a few things we know about the aquifer. One of the challenges with what's happened during the extreme drought, and one of the irreversible consequences of these historically severe droughts and groundwater overdrafts in agricultural areas, is that the aquifers in parts of the Central Valley have collapsed inward on themselves, and so you've lost the capacity, or at least some of the capacity, of these watersheds, of these underwater aquifers to absorb water. And the problem with that is, well, there are a lot of problems with that, but I think in this context, the most relevant piece of it is that there is what you might call pore space in these aquifers. In other words, it's the airspace in between particles of soil and rock in the vertical column beneath your feet. And generally speaking, aquifers aren't giant open caverns of water. I know some people envision them as like underground caves full of water. Those do exist, but that's not really what we mean in most cases when we're talking about aquifers. We're actually talking about all of the airspace that's in between soil particles and rocks in the column of the earth beneath your feet. And so you can imagine that if you extract a bunch of the water from that column, then you lose the water that's essentially stored in that pore space in the aquifer. That aquifer compresses because you're removing volume, and that air, if it's got a bunch of weight of rock and soil on top of it, it's going to compress. And it's not like a sponge. It doesn't just magically uncompress when you add water back to it. To a large extent, the compression of that pore space from groundwater overdraft is at least partially irreversible. It's partly reversible, especially in some places relative to others, but there is some fraction of that aquifer and the loss of pore space to absorb water that just you don't get back, even if you start trying to add water back into the aquifer, as we are this year with all of the water that's sitting on the ground. What this means is that this is essentially why we have ground subsidence in some places, and in a few pockets of the Tulare lake bed, for example, there have been 10 or 15 feet of subsidence of the elevation of the ground over the past 10 to 15 years. So essentially a foot a year for over a decade. That's a dramatic change in the topography, which also increases flood risk and disrupts flood protection and levees, among other things. But it also means that there's a greater propensity for floodwaters to just sit there on top of the ground rather than percolating in once you've lost that pore space. And to be clear, we haven't lost that pore space everywhere. This issue isn't uniform across the Central Valley even. In fact, there's some places where there's very little issue with overpumping and very little issue with ground subsidence, but there are other issues where there's extreme problems with it. And in those places, I think the flood situation is likely being compounded. A question from Pluto. Can you put this year into the context of the seemingly wet and especially cold winter into the context of a warming planet? How likely is a winter like this to occur again? I think that's a good question. And I've been getting it from versions of this from a lot of people. And the answer is actually different depending on which aspect of this winter we're talking about. If we're talking about the fact that this winter was the coldest winter in several decades in many parts of California, I mean, that's legitimately impressive. But it's even more impressive in the context of the fact that winters are about 2 to 3 degrees Fahrenheit warmer in California than they used to be. So imagine how cold this winter would have been if it had happened in a 2 or 3 degree cooler climate. I mean, wow. We're not seeing a trend towards colder winters. We're not seeing a trend towards more extreme Arctic cold outbreaks in California. So the coldness of this winter is actually despite the long-term warming trend, not because of it. All evidence points to years as cold as this year becoming much less likely. In fact, I would not be that surprised if we don't see another winter this cold for another generation in California. It would not surprise me. It could happen. I can't rule it out. But statistically, this is something like a 1 in a 30 or a 1 in a 40-year winter in the present climate, since we haven't seen it in 34 or 40 years. With each increment of warming, it becomes even rarer. So it's pretty unlikely that we're going to see another winter as cold as this one on a statewide basis again anytime soon. When it comes to precipitation, though, it's a very different story. And there's a lot of evidence that climate change is making extreme precipitation events and also very wet winters in California more likely. There's also evidence it's making very dry conditions more likely on the other end of the spectrum. This is in line with that notion of increasing hydroclimate whiplash, or increasing precipitation whiplash, that we termed in some work a couple of years ago. But I think what's key here is that climate change very likely is already playing a role in how wet this winter was. My best back-of-the-envelope guesstimate, informed by prior research and really basic thermodynamics, is that the events of this year are probably about on the order of 10% wetter than they would have been. Range is probably about 5 to 15% wetter than they would have been without global warming, which may not sound like a lot, but it's actually hugely consequential. Because again, keep in mind that when it comes to the impacts from flooding, really all of the relevant human systems, our engineered systems, our flood control systems, our levees and our dams, they're all built to fixed thresholds. They don't magically adjust to the wet extreme as being 10% more extreme. We build them to certain historical standards, and it turns out that a shift in the magnitude of wet events by only about 10% can result in some cases a 50 or 100% change. So essentially a doubling in the exceedance of certain fixed thresholds. So that's different than saying that the events were twice as wet. So I'm not saying that climate change has made storms this winter in California twice as wet as they would have been. I think the number is probably more like 10% wetter. But that 10% wetter might have brought about, say, a 100% increase in the likelihood of seeing conditions as wet as we actually saw this winter. And that would be in line with recent work that we published just last year. You may recall that we published work that I've discussed before as part of this ArcStorm 2.0 project and scenario on the rising risk of a California megaflood. And we did not get a megaflood this year, to be clear. And the events of this year are nowhere near as severe as the plausible worst-case scenarios that we outlined in the ArcStorm 2.0 scenarios, especially the warmer climate future scenario, which is nearly twice as wet with nearly 4 times the runoff of the peak events we saw this year. So again, you ain't seen nothing yet in that regard. But the one lesson I really wanted to emphasize here is that we found that climate change has probably already doubled the risk of seeing an extremely severe flood scenario in California as of 2022. So that's not a prediction about future doubling. Now again, that's not saying that climate change has made California extreme winter storms twice as wet. It's saying that they've made them perhaps about 10% wetter, but in a way that doubles the likelihood of exceeding certain critical historical thresholds. Because again, those are the thresholds that are relevant when we design infrastructure. Everything from storm drains to levee heights and dam operator control curves. Oh, and one more thing. I think the other thing that is a little bit tricky to interpolate is just how much snow we've seen this year in California. I mean, there's been a phenomenal amount of snow. There's been a record amount of snow in some places, especially in the southern Sierra Nevada. In general, climate change is resulting in less snow in California and less snow in the western U.S. in general. There are some interesting exceptions to that. Climate change is bringing about less snow in most places, in most times, at most elevations, except during the most extreme events and at the highest elevations. And again, the reason for that, as I mentioned, is that there are two competing influences. One is the obvious one. As it gets warmer, you're on the wrong side of freezing increasingly often in more places, and some places will see rain rather than snow, or it just gets too warm for the precipitation to fall in frozen form. But on the other hand, as the atmosphere warms, we still have that 7% per centigrade, or about 4% per degree Fahrenheit increase in the water vapor holding capacity of the atmosphere. So the ceiling on how intense precipitation can become increases by 4% per degree Fahrenheit, or about 7% per degree centigrade. So that actually means that you can, if you are still below freezing at a particular time or place, you can get more snow in a warmer climate. So at the high elevations, imagine that you were several degrees below freezing historically, and then you warm several degrees and you're right around freezing. Well, that's still cold enough for snow, and now you got more atmospheric moisture. So you might actually get more snow during the most extreme snowfall events and at the highest, coldest elevations. But in general, I think winters like this year, where we see a lot of snow at low elevations, are becoming even rarer over time. So it's all the more remarkable we've seen so much low elevation snow this winter, because there really isn't any indication that we should expect to see more of that in a warming climate. In fact, very much the opposite. So it really depends what you're looking at. If you're looking at temperatures versus total precipitation and extreme precipitation versus snowfall. So it's a nuanced picture, and there is a climate change signal in some of this, although actually the climate change signal is negative when it comes to winters as cold as the one that we just experienced. So they're becoming less likely in a warming climate, not more. If you excuse me a moment, I'm waiting to sneeze. Excuse me. All right, I'm going to continue with the questions here. There's a few questions coming in along the lines of, why was this winter such a departure from what happened before? And I've covered that in previous sessions. The answer really is that we don't know yet. It could be anything from the Hungatonga volcanic eruption last spring, which injected a record-breaking amount of water vapor into the stratosphere in a way that's not represented well in seasonal forecasts. It could be an unusual transition from La Nina to El Nino. It could be random bad luck. It could be the crazy stuff going on in the Arctic this year. Honestly, I don't know. We don't know. Hopefully we'll find it out eventually, but it's not something I'm going to be able to answer in the near future. Let's see here. Lots of questions coming in, so just excuse my scrolling eyeballs over in the corner of the screen here. There's a question from Fog Machine. I thought El Nino was an equatorial event. Why would it affect California coastal sea surface temperatures? This probably comes from something I said earlier in the conversation. The reason is that although El Nino is a primarily tropical event, it has pretty strong connections to the extratropics in some cases. And sometimes this was something that was kind of cool to learn when I was a grad student and did courses in oceanography. You can get something called coastally trapped Kelvin waves that propagate north and south, respectively, along the western coastlines of North America and South America during El Nino events. And these are something that can result, they don't really transport water, so it's not like there's a current flowing from the tropics to the extratropics, but it's a Kelvin wave, and without getting too much into the details, the reason why this matters is it can suppress the usual coastal upwelling in some of these places. And so the main reason why California ocean water is as cold as it is because there's a lot of upwelling. So water coming vertically upward from the deep ocean to the surface ocean near the coast of California. That's why the waters are so nutrient rich, why there's so much biodiversity in the marine environment in this part of the world, as well as off the coast of places like Peru or Chile in South America. But when you get one of these coastal Kelvin waves, you can inhibit that upwelling for a while, or even for a couple months potentially, if multiple successive Kelvin waves come up the coast. So again, it's not because there's like warm tropical ocean water moving from the tropics to California, but instead it's sort of an indirect effect of El Nino that results in the usual cooling process, the upwelling process, to become inhibited along the coast, and that is what would result probably in the warming of the nearshore waters near California. It's a good question, though. I need to brush up on my my Ekman curves and my nearshore coastal dynamics maybe for this coming summer. It's going to be one of those years. All right, here. I continue down the questions list. All right, got some terms here. Folks reflecting on the terminology. Yeah, there is a lot of pretty wild stuff, floating around out there. In terms of language, and I think a lot of it gets misused and abused in different circles. But on a certain level, I think it's great that people are so interested, and I think that sometimes using the more colorful language is helpful in a science communication perspective, but you do need to present things in context. And so, for example, the term bombogenesis, it sounds like a fake made-up word, right? But it's actually a meteorological term that's been used in the academic literature since essentially World War II era, believe it or not. So this is not a new social media era term. This is actually an old technical term that got rediscovered in the past decade, and because it sounds dramatic, has been bounced around, on social media and in newspaper headlines and such. So, and inevitably, it's gotten exaggerated or overused. But technically, there is a use for it. It does mean rapid strengthening of a storm. In the case of a low-pressure area, rapid strengthening also means rapid deepening, because the deeper the storm, the lower the pressure, the stronger the system. So synonymous are the terms like rapid deepening, explosive cyclogenesis, bombogenesis, the formation of a, quote, bomb cyclone. These are all essentially referring to the same process by which there is a rapid evacuation of air mass from a low-pressure center, forming a rapidly strengthening cyclonic system. That's what that means. That's what happened last week, brought the big storm impacts to coastal California. It's going to happen again tonight, although much farther away from California and with much lesser impacts. There are about 40 or 50 quote-unquote bomb cyclones per year in the northern hemisphere. So they're not rare events. There's usually a few of them per month any given season. But in any one place, they're unusual, and California is not a preferred location for these. They're much more common over the North Atlantic and in the Gulf of Alaska, where they happen every single year repeatedly. But they're much higher impact when they occur near populated places, off the coast of the eastern seaboard, for example, or in the recent instance, right off the coast of San Francisco, where they're much rarer. So I think there is a place for some of this terminology, but it's challenging sometimes because you got to get the details right and the context right. There was some similar terminology wars over the tornado events recently in Southern California, and there was question about whether they were, some initial news headline called them landspouts, which is, again, a real meteorological term referring to a tornado that stems from something other than a supercell thunderstorm. But the problem was, in the case of the tornado that hit LA, it does appear that the thunderstorm that spawned it was at least qualified as a mini supercell. There was a little bit of mesocyclone scale rotation, so that was really more of a traditional tornado. No landspout caveat required. It was just a full-on tornado. It even looked like something you might see in the Great Plains. There was some amazing footage of it, actually, descending from a fully condensed cloud base. So a landspout is something that might happen. Sometimes you can even get landspouts just from tall cumulus clouds. You don't even really need a real thunderstorm. And they're usually much less damaging. They're quite weak. They are still technically tornadoes when they occur, but they aren't violent. They rarely produce major damage or serious injuries or death, whereas more fully fledged tornadoes that come from rotating thunderstorms, known as supercells, can produce serious damage and injuries because the wind speeds associated with them tend to be a lot higher, or at least have the potential to be a lot higher than their landspout counterparts. And in this case, I think it really was a traditional non-landspout tornado in Los Angeles last week. So there's yet another interesting terminology war there. And then there's the question about atmospheric rivers, actually, which is related to some comments I've gotten in my inbox this week, where there have clearly been a lot of atmospheric rivers in California this winter. I don't know exactly how many, and the answer actually depends on exactly how you count them anyway. There is a scientific project known as the ARTMIT project, which is an acronym referring to, I think it's the Atmospheric River Tracking and Intercomparison Model Intercomparison Project, which is literally a scientific endeavor devoted toward figuring out the best algorithm for counting and tracking atmospheric rivers, which should be an indicator that there's actually no consensus on exactly what qualifies and exactly how to count them if you get different answers depending on which tracking algorithm and which data set you use. None of them give grossly different answers, I think. Most people would agree on the big ones. But at the margins, there are some algorithms that count way more things as atmospheric rivers than others. And there's a bit of a divide in the meteorological world whether all such atmospheric rivers are really, truly distinct features from just the ordinary warm conveyor belt in an ordinary extratropical cyclone. I tend to think there is something unique about atmospheric rivers, but I think I can see the point of the other camp, meteorologically speaking, where there are a lot of these events that are more marginal, that we're counting pretty weak quote-unquote atmospheric rivers as atmospheric rivers, and are they truly atmospheric rivers, or is it just the warm conveyor of an erstwhile extratropical cyclone? I can see that argument makes sense, but the reason why I think that some folks who argue that atmospheric rivers essentially don't exist as a distinct feature, I think are also not quite correct, because I think the theoretical counterpoint to that one is that atmospheric rivers can exist in the absence of a parent cyclone. So you can see atmospheric rivers forming over the subtropical Pacific Ocean even if there isn't a major storm driving them. So I think that alone sort of proves that atmospheric rivers can exist as a feature independent of the parent storm, although most of the high impact ones are the ones that occur when those storms attach themselves to atmospheric rivers. So for many of the high impact atmospheric river events, you do need a parent cyclone to come along, pick it up, and bring it into the mix. But perhaps that's a little bit of a deep dive into the meteorology and the inside baseball and the meteorological terminology side of things. But perhaps some folks will find it at least moderately interesting. All right. Looks like I've just about exhausted the questions this time around. So we're right on the hour anyway. So I think it's about time for me to wrap up. and say thanks again. And again, the inbound storm system will be a significant rain and wind event for Northern California, but not as extreme as last week, and targeting different areas farther to the north. Redding could get a bit of a snowstorm tonight, which would be one of the latest on record. Again, remarkable. We're still waiting for the major snowmelt pulse in the San Joaquin Valley. The flooding in Tulare Lake Basin will likely get worse before it gets better. I don't know exactly when that's going to happen, but it'll happen at some point in April or May, probably. And there could be yet more severe convective weather locally in the Central Valley and in parts of the coastal Southern California later this week as this cold late season system spins down there. So would not be surprised to see a few more Central Valley supercells and or another perhaps even a tornadic spin up or two in one of those spots as well. So another active weather week. Things will slowly start to slow down as the season winds down, but it's winding down more slowly than it usually would, and there's no indication of really warm weather on the horizon. So it looks unsettled, pretty cold, and active, at least in relative terms, for the foreseeable future.